And the same thing is again, we can express the vector FL minus 1 of the companion node, that complex number right there. We can express that in terms of the so-called real and imaginary portion. So by that way, then FL minus 1 of R as well as FL minus 1 of capital I superscript, they are both real number. And then finally, even the so-called W raised to the power P, that is the complex number, but that complex number can be expressed as WP corresponding to the real part R, and then this guy here is WP corresponding to the imaginary part capital I. So in this way, again, WPR and WP capital I, they are all real number. So equation 21 that you see on the computer screen over there is nothing except the same thing like the earlier equation that we have. The only difference is we express every complex number into the form of real and imaginary part. We separate it out. Okay. So after we have that, the next step we do will be we just multiply everything out. Like for example, when you have this term multiply with another complex number which is in here, when you multiply two complex numbers, obviously you will have four terms coming out. The first term is come from here times this, the second term come out this times that, the third term coming out from this times this, and the last term come out from this times that. So when you multiply two complex numbers, you will have four terms coming out. And therefore, equation 21 will become equation 22. As a matter of fact, you can see, remember I said you have four terms coming out when you multiply two complex numbers, and they are here. This is the first term, this is the second term, this is the third term, and this is the fourth term when you multiply the last two complex numbers out. Now, after that, we can compare much easier. If you notice, this is I, small I, this is small I. And therefore, what it means is the coefficient of small I, in this case, on the left hand side, it means FL subscript with superscript I. That can be equated to this square bracket right here that you see in equation 22. So that you can equate together, and you can get one equation that have nothing to do with the imaginary number. You get one equation. And then similarly, what you can do, you can see this represent the real component of the vector FLK, and that can be equivalent to this portion right here. So if we equate this block right here, we equate with this FL superscript R, we will get the second equation that have nothing to do with the complex number. So by doing that, instead of having one complex equation that involve with small I, now you have two equations that have nothing to do with the small I, and that is shown in the next slide by equation 23a and 23b. So to summarize it, if you want to calculate, let's say, the value of the intermediate vector f corresponding to the vector level L with the index k. That FLK can be expressed as two number, which is called FL real K and FL superscript I K. You see? In other words, if you want to write a long form, FLK is the same thing as FL real K plus I FL capital I K. So if you express FLK, this guy is a complex number, but that complex number can be expressed in terms of this number FLR and this number FL capital I, and these two numbers are both real number, and the value of FLR, the real number FLR, can be computed based on equation 23a. And similarly, the real number FL capital I superscript, excluding this small I in here, okay, excluding that, can be computed based on equation 23b. So if you look at equation 23a, 23b, we can calculate the value of FLK, and they have nothing to do with the complex number involved. Now, there's the last item I want to explain. We have to, when you compute equation 23a and 23b, we have to worry about the computation of w raised to the power p comma r, and also w raised to the power p comma I. WPR and WPI basically corresponding to, they are the two components of the complex number. So how do we calculate that? Okay, remember in the early day we define W is equal to e raised to the power minus I times 2 pi divided by capital N. That is a definition of W that we told you earlier. Now suppose we want, so this is the definition of W as I show you in the green bracket right there. And so if you have to calculate W raised to the power P, so you raise to the power P on both sides, okay? And obviously this is equal to that, okay? So what we have here, which is e raised to the power minus I 2 pi capital P divided by N, that is the same thing as W raised to the power P. Well, using the so-called Euler identity, again, Euler identity, we can easily express e raised to that power in terms of cosine and sine, where in this particular situation the angle theta actually in this case is right here, 2 pi capital P divided by capital N, just like I mentioned to you in equation 25. And the value of 2 pi is equal to 6.28. So the angle theta, according to equation 25, it is defined as 6.28 times capital P over N. By the way, this W raised to the power P, this is a complex number. That is a complex number. That's in general. But that complex number at the end of equation 24, as you can see, it can be represented as this part. It can be represented as, let me see, go to the next slide. Go to the previous slide. Go to the previous slide. Yeah. So as you can see, the w raised to the power p is a complex number. That complex number can be represented as cos theta minus I sine theta. And what does that mean? That term cosine theta, we call it WP corresponding to the real part R. And the so-called negative sine of theta, you don't have to including the small I, that is defined as WP comma I. Okay? So here I give you the definition WPR and WPI. And you can see clearly if you express in this way, WPR and WP capital I, they are all real number. So what I'm trying to tell you is W raised to the power P is a complex number that can be expressed in terms of two real number components. So now after all those things expressed, then we go back to the previous equation. If you remember we have a four term. This is one term, this is the second term, this is the third term, and this is the fourth term we have earlier. The only thing different is in the previous equation, as you can see, we have something to do with WPR. Okay? Now, instead of WPR, we say WPR is the same thing as cos of theta. And that's why, as you can see on the next slide, instead of calling WP comma R, now we say that term is right here, cos of theta. Okay? And then previously what we have here is like W raised to P comma capital I. Now we say that is the same thing as negative sine theta. So now we have the same previous two equations. Now we call it equation 27a and 27b. So those two equations will help you to compute the so-called f at the vector L level for the index k. So instead of compute FLK, which is a complex number, we can compute the real component of that and the other component of that in here. So that way we don't have to worry about, we don't have to deal with the complex number. And then similarly, corresponding to the formula to calculate FL sub k, we also have another formula that can help you to calculate the companion node. So what is the companion node at the vector L level? What is the companion node of k? That is k plus the distance n divided by 2 raised to the power L. And again, to calculate this companion node, we use the same procedure like the one that we obtained equation 27a, 27b. So that way we can avoid dealing with this complex number by compute the two components of it. Okay? So that is the end of this lecture. Here's the acknowledgement.